A few days ago, chess grandmaster Hikaru Nakamura uploaded a video reacting to a paper written by a stats professor at MIT. The paper analyzed his online win streaks, including one where he won 45 out of 46 games, and whether they were too improbable to be real.
This is an example of multiple testing. That runs counter to what I would think. I should get a coin and flip my coin. If you just do it a couple times, it's not going to do it. But if you do it 10,000 times, it will happen. That's hilarious. That's actually really funny.
The paper was written in response to another grandmaster, Vladimir Kramnik, who's been suggesting that some of Hikaru's streaks are statistically suspicious. But here's what the math actually shows. Kramnik was wrong, Hikaru was right, even if he didn't always follow the stats. We're going to learn today why streaks that seem rare maybe aren't, what a Monte Carlo simulation really tells us, what is farming 2,900 level players and how does it affect the probabilities, and how math can be a mental blocker even for people with the incredible mental horsepower of Hikaru. This is not just about chess. This is about how randomness works when you have a lot of data, and how something that feels improbable, like 45 wins out of 46, might actually be expected. If you've ever looked at a chart or a stat that just feels off and wondered that can't be real, well, you're not alone. A quick recap. Vladimir Kramnik, a grandmaster and former world chess champion, has accused Hikaru Nakamura and others of cheating on chess.com. His argument? Hikaru's winning streaks are so statistically improbable that they could not have happened fairly. But when a professor at MIT wrote a response analyzing the data, what he found was surprising. Not only are Hikaru's streaks not improbable, they're actually exactly what we'd expect, statistically speaking. Hikaru reacted to this on stream. He appreciated the paper, but also seemed to get pretty lost in the math, as did a lot of the commenters and people on the chess.com forums. So let's take a breath and walk through this slowly. The paper uses a simple example to explain how streaks can happen even when everything is fair. And it starts not with chess, but with coins. This is fairly common when talking about probability because we all know how coin flips work and the math is fairly simple given the 50-50 probability of heads or tails. Let's say I hand you a coin and ask you to flip it 12 times. What are the chances you get heads every single time? Well, the chance of getting heads on the first flip is 50% or 0.5. So the chance of getting 2 heads in a row is 0.5 times 0.5. That's 0.25 or 25%, 1 out of 4. 3 times in a row, that's 0.5 times 0.5 times 0.5, which gets you to 12.5%, 1 out of 8. With every flip, that number keeps getting smaller and smaller and smaller, and by the time you get to 12 flips, it's 0.5 to the 12th power. That's about 0.00024, or in friendlier terms, about 1 in 4,096. So yeah, if your friend sat down, flipped the coin 12 times, and got 12 heads on the first try, that would be weird. You'd probably check the coin, ask if your friend had been to magic camp where they learned how to consistently flip a coin, or maybe just ask them to pick lottery numbers for you. That's the kind of number that makes people suspicious. And that's exactly the kind of suspicion that Kramnik is describing. The idea that streaks like this just shouldn't happen if things are fair. So here's the thing. I was taught, and maybe you were too, that humans are just bad at thinking about probability. We overreact to rare events, we find patterns where there aren't any, and no one actually understands the Monte Hall problem even when it's explained over and over again. If you don't know the problem, look it up on Wikipedia, get super confused, then come back to this video, admit I was right in the comments. So one of the best ways to really understand something like this is to simulate it. Don't just trust your gut, don't try to figure out when to apply Bayes' rule versus conditional probabilities. That's just a great way to get lost and intimidated by the math. Just do what I do and what I was taught to do by one of the brightest minds in social science analytics. Just write a little bit of code, simulate some coin flips, and see what actually happens. That's what we're going to do for the rest of this video because I think that's the best way to actually see what happens. It's easier to believe when the computer tells you what's going on than have somebody explain it using Greek letters and formulas you don't understand. So that's what we're going to do. Let's go back to the main stage. So first, we set up how many times to repeat the whole experiment. This code right here my interns wrote says, I want to run this coin flipping experiment 100 times. Next, we define what we're looking for. That means we care about seeing 12 heads in a row before the first tails. The next step initializes our counter. This variable will count how many of our 10,000 trials actually reach that 12 head streak. To make our results reproducible, it's a good practice to fix a random seed, so we do that. That way, every time it runs this code, they get the same sequence of random flips. Now, we start the main loop. And this says basically for each simulation from 1 to 100, do the following. Inside the loop, we reset the head counter for the trial. 1 means heads, 0 means tails. And here's what's happening. We're going to draw one flip at a time. If it's heads, we add 1 to count_head. The moment we see tails, we exit this repeat loop. After exiting, we check whether we hit our target. If that single trial managed to hit 12 heads for the first tails, we increment hits by 1. Once all the 100 are done, we can print the results where it says out of NSIM, simulations, hits, reached, streak target, heads before the first tails. This will output something like out of 100 simulations, X reached 12 heads before the first tails. That's the entire script. It's really simple. The interns did a great job, but there's not much there. That's why they're interns. We just flip coins until tails comes up, we count heads, see how often we get a long streak. So let's walk through this the way the paper wants us to think. Not just about probability in one moment, but about how often you repeat the chance to see something rare. First, we try 100 sequences. Each one is just flipping that coin until we hit tails. Did anyone get 12 heads in a row? Nope. Okay. Let's try 1,000. Still nothing. Okay. How about 10,000? Okay. Here we start to see a few. Just one here, one there, but finally it happens. And that's about what you'd expect. Think about the logic. If the odds of 12 heads in a row are 1 in about 4,096, you'd expect to see it a couple times in 10,000 runs, right? So now let's do 57,000. That's the same number of games that Hikaru has played on chess.com. Now the number of streaks starts to feel normal. It's not suspicious, it's not shocking, it's exactly what the math predicts. And here's the part the paper spells out clearly. Although each specific opportunity has a raw probability of 1 in 4,096, the chance of getting some sequence of 12 heads at some point is a much higher probability. In other words, it's not about whether one moment is rare. It's about how many opportunities you give it to happen. It's still a rare event, but it's not rare to see one over time. Okay, so over 54,000 games, this has an 18.4% chance of happening. Let's slow down and really see where the 18.4% comes from and why the true chance is closer to 70%. First, the theoretical lower bound here. Imagine you flip a coin 10,000 times and break those flips into non-overlapping groups of 12. Flips 1 through 12, 13 through 24, 25 through 36, and so on. Each group has a 1 in 4,096 chance of being all heads. If you have roughly 833 such groups, the chance that one of them is all heads is 0.184 or 18.4%. That's rare, but more like winning a free ticket in a lottery rare than winning the Powerball jackpot rare. That's a neat on-paper estimate, but it misses any streak that crosses a group boundary. Let's look at a quick mini example. Suppose you flip 24 times in a row and you get 7 heads, a tails, 12 heads, a tails, 4 heads. If you check flips 1 through 12, you'd count 0. Same for flips 13 to 24, you'd conclude no streak. But if you slide a 12 flip window across every possible position, 1 through 12, 2 through 13, 3 through 14, etc., 9 through 20, you spot that flips 9 through 20 are all heads. You would have missed that entirely with non-overlapping groups. That's why we run a full simulation. We flip 10,000 coins, scan the entire sequence for any run of 12 heads. In R, we use the RLE function to do exactly that. And then we repeat this process 1,000 times. The result? A streak shows up in about 70% of those simulated runs. In short, that theoretical bound of 18.4% treats only independent back-to-back blocks and gives you a conservative floor of 18.4%. The full simulation, though, with overlapping windows, captures every possible 12 flip segment and finds that those rare runs actually happen about 70% of the time. That's closer to the number of people who report washing their hands after using a public restroom. Certainly nothing you'd go on the internet to express shock about or write a paper about. That gap, from 18% up to 70%, is exactly what multiple testing and overlapping windows do to our intuition. Rare events stay in isolation, but once you give them hundreds or thousands of chances to occur, they become surprisingly common. Don't believe me? Well, let's run the sims. Let's find out. Here's the R code we'll use to flip a coin 10,000 times per trial, repeat it 10,000 trials, and look for any run of 12 heads. We tell R how many times to repeat the experiment, NSIM of 10,000, and how many flips per experiment, N flips of 10,000, plus the streak length we care about. Streak length is 12. Hits 0 equals our counter. Set seed 123 ensures anyone running this gets the same random sequence. Inside the for loop, we simulate 10,000 fair coin flips with the sample code, use RLE to compress a sequence into runs of identical flips, check if any runs of heads is at least 12 flips long, and then if so, we increment our hits counter. After all the simulations, we divide hits by NSIM to get the percentage of trials that contain that 12-head streak. When you run this, you'll see results around 70% matching our earlier discussion and confirming that overlapping windows make rare streaks surprisingly common. Now that we understand streaks and coin flips, let's bring this back to chess finally and the model used in the MIT paper. One of the first things the paper does is look at how likely a player is to win a game based on ELO ratings. ELO system says if two players are evenly matched, then they have an equal chance of winning, though in practice in chess, many of those games may end in draws. A 400-point rating gap, though, gives the stronger player about a 91% win chance. A 1,200-point gap, well, you're nearly unbeatable. In one of Hikaru's most controversial streaks, where he won 116 games in a row, the paper notes that his opponents had an average rating of 1526. Certainly very good for a recreational player, but nothing compared to his own rating of 2800. That's a 1,274-point gap. Using the ELO curve, the paper calculates Hikaru's win probability in those games as about 99.985%, roughly matching Hikaru's intuition that he'll never lose to someone along those lines. Maybe he sneezes, maybe he mouse slips, maybe he gets bored and loses on time, who knows, but we're talking one time out of 1,000 here, 10,000, it's not very much. So we took the same simulation code we've been using and adjusted just 2 lines to reflect the specific case. First, we set the win probability. Probably a win is 0.99985. That's the number from the paper. That's Hikaru's expected win rate based on his rating advantage. Then we changed the streak we're testing. The streak target is now 116. Everything else in the script stays the same. We simulate 10,000 trials, each one representing 116 games, and count how often the player wins all 116 games. The result? The 116-game win streak happens in about 98.4% of simulations. That means a streak that long isn't just plausible, it's almost guaranteed how dominant Hikaru was in that matchup. And the 1.6% of simulations it doesn't happen, it's not suspicious. Again, that's real life creeping in. It's a mouse slip. It's getting distracted by chat running out of time. It's, a half dozen moves in game 94 of a 6-hour stream. You're getting tired, you're bored, whatever. Even a 99.985% win rate, flukes happen. But most of the time, a streak like that is exactly what you'd expect. This is why simulation matters. It's not about defending anyone. It's not about understanding, who's right and who's wrong. It's about understanding randomness and what that looks like when the odds are this tilted. The next thing worth talking about here is to build up your ELO at Hikaru's level is incredibly difficult. There aren't that many players rated that high, and the ones who are, they're monsters. You're not farming easy games at 3,200. You're playing razor-sharp matches where one mistake costs you 10 minutes of focus, 10 ELO points, and maybe 10 more games to recover. And you're doing it against, again, monsters like Fabiano, Magnus, Gukesh, all of these just killers at the top of the game. So what do you do if you're Hikaru? You play down slightly, not to weak players, because that doesn't gain you any ELO, but to a sweet spot just below you. Opponents in the 2,800 to 2,950 range are still elite chess players, but they give you a chance if you're Hikaru to string together some wins and gain a few ELO points at a time. The trade-off, though, is that the math is not necessarily in your favor. You might get 2 for a win, but lose 5 points if you draw it. If you're trying to climb, that margin of error is incredibly small. You can't just play anyone in that range. You want players who are in that range and who are overrated. We want players whose rating says 2,900, but their play says something closer to 2,700. And here's the thing, for you and I, who can begin to tell the difference? But at Hikaru's level, he can tell. After a few games, he can spot whether someone is holding their own or whether they're slipping just enough for him to press the gas and keep going. That's when the farming starts, not with random matches against equal players, but with careful strategic selection. Once he finds someone who gives up ELO and can't quite keep up, he just rematches them again and again and again until the edge disappears. So when we see a crazy looking win streak, we can't just ask, how likely is this if this opponent is like 2,900? We have to ask, how likely is this if the opponent is actually worse than their rating suggests and Hikaru knows it? Everything up to this point is about how Hikaru creates these streaks. It's not just about coin flips, it's about setting yourself up for success.
Like in recent times, like you'll notice that I always play people who are like 400 points below, like 29 something. I wish someone would find a way to just like look and do an actual mathematic calculation of how many people are like way overrated. Because I think there are a lot of people overrated between 2800 and 2950 who you can just like, I can just beat them with my eyes closed. I still believe that.
In the video, Hikaru says he identified the 2800 to 2950 range as the sweet spot for boosting his elo. Strong enough to give him points, but often beatable enough to farm. And within that range, again, he's not picking opponents at random. He's using his incredible abilities and experience to figure out who's slightly overperforming their true level, capitalizing on it by farming them while avoiding players who are tougher to beat. This actually makes the math really tricky. We can't assume every game is played under neutral conditions. Hikaru is intentionally creating favorable conditions over and over and over again. And when you do that across thousands of games, unlikely things stop looking so unlikely. Not everything is Title Tuesday playing a progressively harder opponent potentially every match, not playing against top players. And this is such an important distinction to remember. I don't think anyone, including Hikaru, believes he would win 46 out of 47 games if the matches were evenly balanced. But that's not what's happening. He's playing opponents where he has a huge advantage. And when you do that at scale, streaks that seem impossible start to look a lot more ordinary. Okay, so we've talked a lot about the logic here. Let's run some simulations to see this mathematically. I don't have the data set of the actual games like the original author did, but we're going to make some simplified assumptions to demonstrate the basic idea. So let's test that and a couple other things. Here's the R code to simulate this 54,000 game career with this opponent mix. Check to see if any 47 game window contains at least 46 wins and no losses. In this setup, where Hikaru has no control over replays, the 46 win streak basically never happens. Even over 54,000 games, the combination of tough opponents and small margins means these streaks are extremely unlikely. In our sims, it showed up 0% of the time. This contrast is the entire point. If you assume neutral results, you get surprising results. But if you model how Hikaru actually plays, selecting opponents he can beat and playing a bit, the math shifts. So streaks that look suspicious under one assumption become normal under another. You don't have to believe me though. Let's look at R. Let's imagine a world where Hikaru is not selective at all. He's not farming or rematching, he's just playing whoever online. A random mix of top players, some are on his level around 3200s, some are slightly below, strong 3000s, and some are quite a bit weaker, players around 2800. That's a pretty fair assumption if you think online chess is just a global leaderboard and everybody's queuing up to play anybody. So we simulated it. We gave Hikaru a balanced diet of opponents, 1/3 at 2800, 1/3 at 3000, and 1/3 at 3200. Let's pause and look at the code here. This time the R script uses a fast rolling window logic to count win streaks efficiently. Here's what it does. First, it randomly assigns each of the 54,000 games to one of the three opponent types, 2800, 3000, or 3200. Based on that, it gives each game a different probability of being a win, a draw, or a loss. The 2800 games are most likely to be wins. We use 85% for those. The 3000 games are more balanced, about 68% win. And the 3200 games are true toss-ups, 30% win, 40% draw, 30% loss. We then use a fast rolling check to see if there's any 47 game stretch with at least 46 wins and no losses. That's the standard we're using because the controversial streak in question was 46 wins and 1 draw. And here's what we found. Given these assumptions, 0% of our simulations produce that kind of streak. Not one. If Hikaru is playing a mix of equals and slightly weaker players, streaks like that don't happen. The math doesn't support it. But now let's make a small change. Let's say Hikaru avoids the top tier players, no more 3200s. Now he's only playing 2800s and 3000s, half and half. We run the exact same R script before, the only thing we change is the opponent mix. This time, 32% of simulations show that 46 and 1 draw streak. That's a big jump. A little bit of strategy makes this plausible. Finally though, we modeled a world where 3/4 of his games are against 2800s, and that's consistent with how Hikaru describes his own play. He says, I think there are a lot of people who are overrated between 2800 and 2950 who I can just beat with my eyes closed. It's okay. Same code, same 54,000 games, same streak threshold. This time, that 46 win streak showed up in 74% of simulations. It's not just possible, it's likely, and it's more likely to happen than not. All we changed was the opponent mix to be closer to what a player like Hikaru might be doing and the strategy he said he uses. So what did we learn? We started with a question. Is that 46-1 streak really so improbable that it needs an explanation beyond just incredible skill? We broke it down not with hot takes, not with rants for the internet, but with probability, code, and some careful thinking. Let's pause for a second and talk about something that stood out to me in Hikaru's reaction to the paper.
The curve fit should be done excluding games played by me. Okay, whatever. What do we get? More math.
It wasn't just that he disagreed or agreed, it's that he looked really uncomfortable. He called the math gobbledygook a few times, said he wasn't a math guy, they didn't understand what any of it means, and honestly, that's not unusual. Even brilliant, analytical people who can calculate dozens of moves ahead in a chess game, can shut down in the language shifts to formulas and probability. It's wildly impressive to me to watch people like Magnus and Hikaru play 4 boards blindfolded, and when they talk about just the next moves, I can't even make up chess moves as quickly as they can talk about them and see them. This is not about intelligence. It's about self-efficacy. It's the belief that you can make sense of something. And if Hikaru, with world-class instincts, absurd pattern recognition, in the top 5 of his profession, feels like stats are a foreign language, then it's no surprise that so many other people do too. It's a really good reminder, if the goal is to help people make better decisions with data, it's not just about getting the math right or even maybe getting the math right. It's about making the math feel usable. And that's what we try to do on this channel. If you want to be good at that, keep watching. Enough of my soapbox, but something I just really want to talk about. Let's go back to the main stage. Along the way, we learned that rare things aren't actually that rare when you try them often enough. We learned that win probability depends on who you're playing and how often. We learned that simulations are sometimes more honest than our intuition. And we learned that streaks don't always need a story. Sometimes they just need context. We also looked at how hard stats can be to read, even for someone brilliant in one domain like Hikaru. Why part of explaining data isn't just showing the numbers, it's helping them make sense. At the end of the day, this wasn't about proving anyone right or wrong. It was about understanding something complicated and clearly. This wasn't luck, it was volume, strategy, and probability. Thank you for watching. If you're into clear answers, not guesswork, like and subscribe to this video, and I will see you next time.